And he's going to give us a discussion of astrophotography, and even here we've also got some highlights of his that he's taken from a telescope here at Penn State. So let's all give a warm welcome to Evan Bray.
You said the first talk I started talking about astrophotography.
Hello, testing. Okay, my name's Evan Bray. I'm a graduate student here. One of my favorite hobbies that I've picked up since starting grad school here is taking pictures of things in space using equipment and telescopes that we have on the rooftop of Davy Lab. I am not a professional photographer in any way. The only camera I own is the one attached to my cell phone. So I'm coming at you here with how to take pictures of things from space, as told by someone with very little photography experience. And my goal here is to kind of focus on how taking pictures with telescopes is different than taking pictures of things with a handheld camera. So my outline for this talk is that it's kind of broken into two parts. The first part, I'll talk a little bit about the raw ingredients that you need to make a pretty picture in the first place. And the second part will be how you mix those raw ingredients together to get a pretty picture out in the end. And the working example that I'll use here is an image of the Whirlpool galaxy, Messier 51, shown here on the right. And we'll use some exposures that I've taken of this object in various stages of processing throughout this talk, and you can see how the image will evolve as the talk goes on. A good first question that a lot of people have about astrophotography is how long you need to make your exposures for. Obviously, you need to make your exposures very long because things in space are very faint. So to answer the question of how long you should expose for, the answer is as long as possible. But there are two caveats. The first is that you don't want to see star trails, like you see here. And the second, which I'll get to in a minute, is that you don't want to saturate your image and get something called blooming, or reaching full well is what we sometimes call it. So with these star trails, though, the cause of star trails is that the sky is moving while your camera, which is attached to Earth, is remaining stationary. Or more accurately, the stars are remaining stationary while the Earth is spinning underneath of it. And we can avoid star trails by using a special type of telescope mount. There are two main types of telescope mounts. The first one here on the left is called an alt-az mount. They're cheap, they're easy to use and set up, they're usually very light, and they're very intuitive for a first-time astronomer to use. The downside is that you get star trails in your images when you try to take long exposure shots with it. You also can't observe things that are directly overhead. The type of telescope mount that we use for serious astrophotographers, though, is something called an equatorial mount, which is shown here on the right. And the advantage of that is that you don't have star trails because it effectively cancels out the rotation of the Earth. And it does that by aligning its rotation axis parallel to the rotation axis of the Earth. It's this blue line here. The downside is that every time you move the telescope, you need to realign it to the North Star. These types of mounts are also more expensive, and they're less intuitive to operate by hand. But a quick aside, this image that I showed you 2 slides ago with the star trails in it, I can actually tell you how long of an exposure it was that they used to make that photo, just by doing some quick geometry. We know that the sky makes one complete rotation every day, and we know that the stars in this image have moved 1/360th of a rotation. So that means that the images used to create this photo were taken over about 1/360th of a day, or about 4 minutes. The second caveat to how long you should make your exposures are that you don't want to saturate your image. That is, you don't want to reach something we call full well and start blooming. And I have an example of that here on the right. In the top right, I have a short exposure of a bright star, and in the bottom right is the same star, just with a slightly longer exposure. Now, the term full well comes from comes from the definition of, or comes from the workings of how the detector in your camera works. Your camera is composed of lots of pixels, and you can think of each pixel as a bucket for light. The bucket collects light, and when the bucket fills up, it overflows into the neighboring buckets, which is why you get this streaking up and down. Your cell phone or your handheld cameras probably don't do this because they have extra features built into them so that this doesn't happen. In astronomy, our cameras don't have those features built in because we choose to not build them in, usually. That's not always the case. But I'll get back to that in a minute. Okay, astronomical cameras are built fundamentally different than cameras in your cell phone or a handheld camera. And the reason for that is that astronomical or astrophysical sources are very faint. So we need to collect as much light as possible. We use that by using big telescopes and special cameras composed of large pixels. In your phone, each pixel in your phone's camera is composed of a couple smaller subpixels or smaller buckets that are used for collecting light of a certain wavelength. And wavelength ranges that correspond roughly to what the colors we call red, green, and blue. The reason that there are 2 green subpixels in each pixel of your camera is actually biologically driven. The reason for that is human eyes are very, very good at picking up green light. And they're also very, very good at picking up small changes in the amount of green light that something emits. So if you want the pictures that you take with your phone to look realistic, your phone needs to also be very good at picking up green light. And we do that, or your phone camera does that by having a larger collecting area for green light than it does for red and blue. For our astronomical cameras, though, our pixels can't tell the difference between individual photons of a different color. So that's called having monochrome pixels. So the whole pixel is sensitive to all different kinds of light. The upside of that is that we can choose what wavelengths of light we want to be sensitive to by covering the camera with certain filters. The downside of this is that we lose the ability to take one-shot color photos, one-click color photos like on your phone. But that's okay, because that's not what most of astronomy is about anyway. Oh, I'm sorry. We have these large monochrome pixels. The reason that we have to worry about saturating our images is because a lot of times our cameras are built in such a way that we don't have this anti-blooming, anti-saturation technology built into them. Because we want to have pixels that can hold as much light as possible. We want our camera to be composed of large buckets. The second raw ingredient that you need for your images, besides the raw exposures themselves, you need flat fields. And the purposes of flat fields are to calibrate out imperfections in your final image. Imperfections that could be caused by the telescope not evenly focusing light across the detector. This causes an effect called vignetting, and it causes the center of the image to be brighter than the edges. We also worry about diffraction effects on the surface of the detector, which in this image you can see as these diagonal lines running across the detector. We also get dust specks that land on the mirror of the telescope, which cause these donut-like effects to appear. And by taking flat fields, we can make sure that those final imperfections don't appear in our final pretty image. We also need to take something called dark frames. The term dark current describes the rate at which random electrons are generated in the image sensor of your camera. It causes your images to look grainy and blurry. So in order to minimize dark current, we cool the camera down to be very cold. So when the camera is very cold, the rate at which these electrons pop into your camera decreases. It's very sensitive to temperature, so a lot of times professional astronomers at professional facilities will cool their cameras down to liquid nitrogen temperatures, which is about 77 Kelvin. All right, that concludes the first part of the talk with the raw ingredients. Now I'm going to talk a little bit about how you can combine them to get a pretty picture out in the end. This is a rough outline of the steps you need to take, where you subtract your dark frames from your main exposures, divide by the flat fields to get rid of the imperfections, align the individual images because the telescope wiggles a bit between individual exposures, and then you stack them together to get a color photo. Let's step through that though. The first step, subtracting dark frames, gets rid of unwanted background from the random generation of those electrons that you don't want, and it also removes hot pixels. Hot pixels are something that aren't as common in regular photography because hot pixels are caused by basically defective pixels in your camera. The reason you have to worry about those in your cell phone camera are because there's a much higher level of quality control when you're making 100 million small cell phone cameras at a time, as opposed to one ultra expensive astronomical camera. So when you're mass producing cameras for cell phones, you can afford to throw out half of them because they have hot pixels in them. That's not the case when you're making one camera at a time. At this scale, you can't see the difference very well, but you will in one of the later slides. The next step is dividing by your flat fields in order to get rid of those imperfections. I have a raw image up here on the left, as well as the flat field that it's divided by in the bottom left. And you can see some diagonal striping and some vignetting in this image in the top left. And on the right here, we have what it looks like afterward. It's much more, it's been flattened, you could say. It's no longer brighter in the middle than it is at the edges. That's the most prominent effect. Once you've processed all your images with those steps, the next step is to align your individual images. And we do this by locking on to things in the image that we know aren't moving. In our case, we use stars. So we use a special computer program that locks onto the center of each one of these stars and compares the location of these stars in every single one of our images. The telescope is very steady and it can follow the object across the night sky, but it does wiggle a little bit. And if we move forward without aligning our images, our final picture is going to look more blurry than it needs to. Once we've aligned all our images, we combine everything into a final product. We sometimes refer to this as median combining, depending on what technique you want to use. So on the left, there's a short animation showing a bunch of individual aligned exposures. And on the right is what happens after you perform this median combine. Now, what I want you to notice in this image on the left is that even though the locations of the bright points, like the stars and the galaxy itself, aren't moving, there's a grainy background, which is changing in intensity or distribution, or just it's flickering a little bit between images. Once you perform this median combine, all of those imperfections tend to level out, and you get a background that's much more uniform and dark. Okay, so you can see it at this scale. I've purposely done something incorrectly with this image on the right, and it was on purpose, I promise. That you can see these large bright points of stars, but there's a lot of other small bright points scattered throughout the image, also kind of grainy. And those bright individual specks are hot pixels. And if you don't do that dark subtraction that I mentioned a few slides ago, your final image has these white flecks scattered all over it. That's just to emphasize the importance of doing your dark subtractions. The last step we take is that we want to really make the object that we're trying to photograph pop. And chances are, if you're imaging something like a galaxy or a nebula, it's way, way fainter. It's much more faint than the stars in front of it. So we play with the contrast levels to make the object in the middle pop out. Sometimes that's referred to as doing a log stretch or log scaling the image. And what that means is that we do a little bit of math on each pixel in the image. Because the galaxies of the nebula are all very faint, we want to increase their brightness in comparison to the stars. So the stars are the brightest thing in the image, without a doubt. So we decrease what we call the dynamic range for the stars, while increasing the dynamic range for the galaxies. And what this means is that in comparison to the stars, the galaxy now looks much brighter when compared to the stars in your frame as well. So everything that I mentioned here was just for a single color, and you need to do this for at least 3 in order to get a pretty picture out of it in the end. So go back and repeat these steps 3 times. And for the rest of this for the previous part of this presentation, I was using blue frames. Go back and do it for red and green, and I've shown the final product for each one of those steps here, and then align them to one another and stack them up, and you get a pretty picture out of it in the end. So this is my final slide. I'll leave this up here. just to give you a sense of what the individual components look like before they get combined. And thank you for listening. Yes?
So you mentioned the procedure of subtracting the dark and dividing by the flat field. How do you collect the dark field frames and the flat field?
So the question is, how do you collect the dark frames and the flat field frames? Dark frames are easy. You just you want to ensure that the camera is taking exposures in an as dark environment as possible. You can do that. Usually you do that by keeping the shutter of the camera closed while you take your exposure. So you take a 10-second exposure, but the trick is that the shutter of the camera never opened during that 10 seconds, so no light got in. Also, I recommend against using any flash photography while you're taking these dark frames. You want the room to be as dark as possible. Flat fields are a little trickier. In order to take a good flat field, you need to look at an object that's uniform in brightness. The sky by itself is not uniform in brightness, especially at night, because it's flecked with stars. It's flaked with stars everywhere. How I take my flat fields, and I think a lot of professional astronomy facilities do as well, is that they wait until sunset, and at a very specific window right around sunset, they look in the opposite direction of the sky and 30 degrees up in altitude, because at some point in time somebody decided that that is the most uniform brightness patch of sky, and you take a bunch of exposures of the sky at that point. It's uniform brightness. The telescope isn't following the sky, and it allows you to uniformly illuminate your telescope with light, as opposed to looking at stars or something. Great question. Yes.
In a lot of professional observatories, there's a white panel on the wall that's then used for shooting flats. Us amateurs put T-shirts across the front of our telescopes and point to the blank piece of sky.
The comment was that in a lot of professional astronomy facilities, they also have these special white panels on the walls, so that you're not just limited to doing this at sunset. You can do it anytime, or just a T-shirt, like you mentioned, white T-shirt.
How long are your sub-exposures?
Depends on the object I'm looking at. Usually, I'm sorry. The question was, how long are exposures do I take in my photography? Usually between 30 to 60 seconds. I'm usually limited in how long I can expose, because the bright stars in the image will start blooming up and down the image, and I want to minimize that. I want to minimize that.
You guide at that kind of time?
The telescope is guided for the 30 to 60 seconds, and it guides quite well. Sub-arc second.
Separate guide camera.
Yes, with a separate guide camera.
So you guide on the stars, track.
That's correct. Yeah, we have a separate smaller camera that if you want, you can lock onto a bright star outside of your field of view and use it as a guide to help the telescope accurately follow your image across the night sky.
Do you expose the green longer to make it more like humanizing?
The question is, do I expose longer on green than in other colors? And I'll expand that question and say, do I have longer exposures of different colors than others? And the answer is yes, although it's not. I usually spend more time taking images in with a blue filter than a green. And the reason for that is because blue light is harder to come by. The atmosphere attenuates, the atmosphere removes more of the blue light than it does of the green or the red. And so if I want my image to look as pretty and as and as smooth as possible, I need to spend more time gathering blue light than I do green or red. Good question.
Combining the images, there's somewhat of a arbitrary so you have a rule of thumb of what you're using for your thing.
Okay, that's a really good question, and something I particularly enjoy about astrophotography. As I take these three images, the question is, how do I, what rule of thumb do I use when combining my images of blue filter, green filter, red filter? And the answer is that a lot of this is if you want it to be, it can very much be in the eye of the beholder. So what I do for most of my images is that I stack these together and I get an image that looks like this but not quite. Then in Photoshop, I play with the individual intensities of the blue, red, and green light until I get an image that looks aesthetically appealing to me. So what you can do, what you can do, and it just doesn't always produce images that look better, is that you can make sure that you have a star in your field of view that is certified white, and you can white balance on that star. And that's how you'll know that the colors you're seeing from your galaxy or nebula are as realistic as possible. That doesn't always, and that is a certain level, takes a certain extra level of processing and difficulty, but there's no guarantees that it will produce an object that is better looking, I suppose.
Mm-hmm.
Yes.
So what types of objects have you photographed and do you have favorites?
The question is, what types of objects have I photographed and what are my favorites? Galaxies are my favorite. I think so I've photographed galaxies and nebula and star clusters usually. Galaxies are my favorite because I really enjoy being able to. I think there's a special quality in being able to look at a picture and know that there are 300 billion stars contained within the frame of that picture, and comparing it in your head to the size of the Milky Way. I think that makes people feel a certain way. My favorite picture that I've ever taken was not a particularly pretty one, but it was a particularly fun one. It was of a galaxy called NGC 262, and NGC 262 is the largest spiral galaxy in the known universe. And we can, it's 200 million light years away, and it's very faint but visible from State College here, which I think is quite impressive. So I did a bunch of 5-minute long exposures at this point in the night sky where the galaxy was supposed to be, and I couldn't see anything, but I spent an hour or two doing that. I took all these pictures and I combined them together, and only once I had combined together these 2 hours worth of pictures did a very faint spiral pop out. And this wasn't a color photo, this is a black and white photo just because I wanted to see if it was possible. And the reason that's my favorite image is because after all this work, this very faint spiral just barely popped out. And I know that that spiral galaxy is the largest spiral galaxy that in the known universe, and it's the 5th largest galaxy in the known universe overall. So, we're talking 10 Milky Ways side by side. You can fit inside this galaxy, and it contains as much mass as the Milky Way and its 54 closest neighbors. So it's a big boy. Yes?
Get the light pollution of State College, do you ever shoot narrowband?
I've tried. I haven't had any luck. The question is, have I ever shot with narrowband filters? Usually, so these images were taken with a blue filter, green filter, red filter, but you can get very specific filters that only let in very specific wavelengths of light. And sometimes that can be helpful for taking pictures of things like nebula. And unfortunately, it's not helpful enough. So I haven't found it to be useful here.
It's a tough place to work.
It is. Yes, Mike?
Have you tried images of the sun?
The question was, have I tried taking pictures of the sun? I have not, and the reason for that is for the same reason that you wouldn't look through a magnifying glass at the sun, because it would be very damaging to a bunch of very expensive equipment.
With a narrowband filter?
This is true. The answer to the question was try using a narrowband filter. However, what happens then is that you melt through the filter.
Still not a broadband filter across the front of the
Yeah.
temperature.
For the same reason, we don't look at the moon with the 24-inch telescope on the roof.
Also, your advisor owns that telescope.
Or as part of, one of the people that uses on the roof. That's right, yeah.
Let's thank Evan again.
Thank you, everyone.